we looked at putting quadratic functions in vertex form. So quick little reminder, you could complete this square. So I would probably subtract 3 from both sides and then figure out how can you rewrite x squared plus 2x plus some quantity as a perfect square. So if you figure out that number is going to be 1. And then you could rewrite it in factored form as x plus 1 quantity squared. Subtract 2 from both sides and have it changed to vertex form. So that's all fine and dandy if it's one that's decent to convert to vertex form. That one, completing the square, was nice whole numbers. It is another option to use the fact that if you have a quadratic in standard form, your x-coordinate of your vertex is going to be negative b over 2a. If it helps you remember, that does have a relationship to the quadratic formula. It's the part of the quadratic formula without your square root. So maybe that'll help you remember your value for it. Okay, so we're going to use that fact to find the vertex of this quadratic function instead of completing the square. So my value for b is negative 2, my value for a is negative 3. If I plug those in to get the x-coordinate of my vertex, I'll come up with 2 over negative 6, which is going to reduce to be negative 1/3. And then to get my y value, because that's only half my point's coordinates, I'm going to need to plug that back into my original function. So if I plug negative 1/3 into my original function, it's going to be a little bit messy to calculate. You'll end up with 1 1/3. So your vertex is at negative 1/3, 1 1/3. I could go ahead and plot that on my graph. It's not going to be absolutely perfectly in the right spot here because my scale is a little bit large to make this fit nicely. Okay, I need additional points. So if I plug in, say, 0 and 1, because those are pretty close to my vertex, I'll get 1 and negative 4. And then I could reflect it over my axis of symmetry, which is the line x equals negative 1/3. Be kind of careful. Technically, if I'm at negative 1/3 and I reflect that one over, it's going to be at negative 2/3, 1. And then that one won't be quite over to negative 2. Draw that in. And then I was also asked for my x and y intercepts. So let's start with my x-intercepts. I could estimate based on my graph. Looks like maybe negative 1 and 1/3 or something, but we want exact values to see where it crosses my x-axis. So I could set this equal to 0 because I know that my y value for an x-intercept is 0. I'm going to go ahead and divide both sides by negative 1 because I like to factor or use the quadratic formula when it has a positive coefficient on my x-squared term. This one actually factors nicely into 3x minus 1 and x plus 1. So if I set each of my factors equal to 0, I'll get x values of 1/3 and negative 1. Hey, my random estimates were actually correct this time. So there's my x-intercepts. My y-intercept I already actually found in my table because I plugged in an x value of 0 and I got a y value of 1. So that's the point where it crosses the y-axis. Domain is from negative infinity to infinity. It will be always on our quadratics. And range is from negative infinity up to 1 1/3. We're going to do a little analysis of some quadratic function graphs now. So first off, I'm looking for my maximum value. That's the largest possible output that my function can give me. So if I find my highest point on my graph, it has a y value of 2, so that's my maximum value. And the x value that it happens at is 1. This one opened downwards, so it did have a highest or maximum value. If I had one that opened upwards, it would have a minimum value instead. On B, I'm looking for the number of real solutions to the equation f of x equals 0. Or essentially, I'm looking for what x values give me y values of 0. So if I think about my points on my graph here, if I find the points that have y values of 0, those are at 0, 0, and 2, 0. So there are 2 x values that give me output values of my function of 0. So there are 2 real valued solutions to the equation f of x equals 0. Specifically, I even know what they are. They are the x values of those points So x equals 0 and x equals 2. Remember, I can only see real valued solutions on my graph, so if this didn't have x-intercepts, it might have non-real complex solutions instead. If I'm looking on part C for how many real solutions there are to the equation f of x equals 3, well, think about the horizontal line that contains all the points of y values of 3. My function doesn't reach up that far. So there are no x values on this function that'll give me an output or a y value of 3, so there are no solutions. I'm going to write an equation in vertex form to match my graph here. So let me start with kind of a blank vertex form equation. So there's general vertex form right there. I need to figure out the values of h, k, and a. So h and k come from my vertex, which is my point 2, -9. So let me substitute those in. So I'll have x minus 2 quantity squared minus 9, which if you think translations, my vertex is shifted right 2 and down 9, so that does correctly match those transformations. Then besides my vertex, I also have an additional point that I can substitute in x and y values from, and then I'll be able to solve for a. So let's plug in those x and y values for x and y in my equation. And then if I go ahead and do 0 minus 2 and square it, that's 4 times a minus 9. Add 9 to both sides gives you 8, and then divide by 4 is going to give you a value of 2 for a. So my function has a vertical stretch of 2 as well. If you go ahead and write your final equation, just copy and paste it a little bit here, I'm going to have 2 times the quantity x minus 2 squared minus 9.